This video will cover section 2.6 part 2, and it is very important that you watch this video because I will not be able to cover this material in class. We are very limited in time, and so I would rather you watch this video at home so that we can get started and finish with chapter 3. So this is where we left off on section 2.6. These problems were not included on the exam. However, they are still going to be included in the homework. So what we're going to do is be using function transformations to graph rational functions. And what we could see from the graphs that we have here, we have the graph for 1 over x. Remember that is the reciprocal function, and it is the simplest rational function. What we know about that function is that it is odd, and that is because if you substitute, if you try to find f of negative x, you will get 1 over negative x. So we could say that f of negative x is the same as the original function, but with an opposite sign. So because of that, we say that the function is odd. And odd functions, remember, they have symmetry with respect to the origin. Now, we also have the function 1 over x squared, and that is the one that we're going to be graphing using transformations. And that function, it happens to be even. And that happens because if you find f of negative x, you will have f of negative x inside parentheses and then square. And so we all know that that turns into 1 over x squared. So because we could say that f of negative x is equal to f of x, the original function, the function is even. And remember that even functions are symmetric with respect to the y-axis. So what you can see here is that every point is reflected across the y-axis. So we have positive 1, 1, and we also have negative 1, 1. Similarly, we have the point 2, 1/4, and we also have the point negative 2, 1/4. So that it needs to be symmetric with respect to the y-axis. Now, what I'm going to do is use some of those points and then transformations. Now, to just do a quick review about transformations, we have here a +1, and that +1 tells us that there is a vertical shift of 1 unit up. And we also have a horizontal shift, and those are counterintuitive, and that horizontal shift is given by that negative 2. And so that means that the function will move 2 units to the right. Now, let's see what it is that we have to do. And if I remember correctly, we first need to do the horizontal shifting, and then at the end we do the vertical shifting. So for the horizontal shift, we're going to get the some of those original points. Well, first let's establish what we're going to do. With the moving the function 2 units to the right, that implies that we're going to add 2 to every x value. And moving the function 1 unit up, that implies that we're going to add 1 to every y value. So what I'm going to do is write down the original points of the parent function. And so we have negative 2, 1/4. We also have the point negative 1, 1. We have the point negative 1/2, 4. We have the point 1/2, 4, 1, 1, and we also have the point 2, 1/4. This does not mean that those are the only points on the graph, because we know that the graph is actually continuous. It is, the points are connected. So those are just 6 of the points that belong to the graph that we're going to use on our transformation. So let's do first, we're going to do the horizontal shifting. So we're going to add 2 to every x. So if we do that, we will come up with the points. Negative 2 plus 2 will be a 0. The next point, negative 1 plus 2, will be a 1. And then we have negative 1/2 plus 2 3/2. And then we have 1/2 plus 2, so that will be, remember that 2 is equivalent to 4/2. So 4/2 plus 1/2 is equal to 5/2. The next point is going to be 1 plus 2, so that will be 3, 1. And then finally 2 plus 2, so that will be 4, 1/4. Now remember that it's only given us the horizontal shift. But now we need to do the vertical shift. And in fact, we could have done both at the same time, but I didn't want to get you confused. So I'm going to make some room here so we can write down the other points. Now we're going to add 1 to every y coordinate, and the x will remain the same. So we'll have 0 plus, remember 1 is equivalent to 4/4. So 4/4 plus 1/4 is equal to 5/4. And then 1 plus 1 is 2. 4 plus 1 is 5. 4 plus 1 is 5 again. And then 1 plus 1 is 2. And the final one, we will have 1/4 plus 1, so that will be 5/4. Now, based on that transformation, remember we do have two transformations, a horizontal shift of 2 units to the right, and a vertical shift of 1 unit up. So based on that, I'm going to go ahead and plot my points, and that will give me the transform function. So we start with 0, 5/4. Somewhere there. And then we have 1, 2. 3/2, 5. 5/2, 5. 3, 2. And 4, 5/4. Now, if you look at the original function, there is a vertical asymptote on the y-axis. And that is, it happens because we know that x cannot equal to 0. Also, we know that this function is bottom heavy, so the vertical asymptote will be the same value as the exclusion from the domain, but the horizontal asymptote, since the function is bottom heavy, it is automatically y equals 0. The transform function that we have here, actually my graph is a little off. So let's talk about that. So for the transform function, we are saying that we're moving our graph 2 units to the right. So the vertical asymptote, instead of being at x equals 0, will also be shifted 2 units to the right, and therefore it will be x equals 2. That's the vertical asymptote. The horizontal asymptote, the parent function had it at y equals 0. So since this function is being shifted 1 unit up, the horizontal asymptote will also be shifted 1 unit up. So instead of being at y equals 0, we'll be at y equals 1. So I need to consider that when I graph my function. So the horizontal asymptote will be here. And the vertical asymptote, it will be here. Also, it makes sense if we look at the equation, we know that 2 must be excluded from the domain. remember to find the domain, you take the denominator and you say that cannot equal to 0. So if we take the square root here on both sides, we will get x minus 2 cannot equal 0, and so x cannot equal 2. So remember, that same exclusion from the domain is going to be the vertical asymptote on your graph. So let's go to, well, just to finish up the graph. The line of the graph will get close to the horizontal line y equals 1, but it will not touch it. If we were using arrow notation, you could see that as x approaches 0 from the left, the function value approaches infinity. Not equals, I'm sorry, but approaches infinity. And if we look at what's happening as x approaches 0 from the right, we will say that f of x approaches infinity. So just as a little preview for when you take calculus, if you were asked to find what is the limit of this function as x approaches 0, and here we could consider the right limit and the left side limit to be equal. So in this case, the limit will be infinity. So let's go to the next slide. And here we have steps to graph a rational function. And so let's go over them quickly. So steps or strategies. So we're going to refer to p as the numerator, q will be the denominator. And remember, those two are polynomial functions. So first, one thing that is kind of useful, it will be to determine if the function has symmetry. So if the function is even, it will be symmetric with respect to the y-axis. If the function is odd, it will be symmetric with respect to the origin. Now, to find the y-intercept, if there is one, remember sometimes the y-axis might be the vertical asymptote. So to find the y-intercept, we already know we must let x equal to 0, and so that's why they're saying here find f of 0. Now, to find the x-intercepts, if there are any, remember there may not be any x-intercepts if the y-axis is the horizontal asymptote. So to find the x-intercepts, you have to find, solve the equation. And here there's a little shortcut. So if we have the function f of x is equal to p of x over q of x, remember that to find the x-intercepts, we always say you let y equals 0, the other letter. So if we were to do that, we know that f of x is equivalent to y. So if we let this f of x equal to 0, and we have p of x divided by q of x, and then we try to solve for x, so you could see here that q of x is dividing p of x. So we all know that if we take this quantity across, it will be multiplying, because on the right side it is dividing, so if we take it to the left, it will be multiplying. So 0 times q of x equals p of x. And we all know that q of x times 0 is equal to 0. And so that is why the strategy that we have here to find the x-intercepts is being reduced to just solving this equation. So you will equal p of x, which is in this case representing the numerator. So you take the numerator, equal it to 0, and then you solve for x. That is just a little shortcut. Number 4, it says find any vertical asymptotes. So to find any vertical asymptotes, remember, those are the numbers that you exclude from the domain. Or in other words, you take the denominator, equal it to 0, and then you find the x values. To find the horizontal asymptotes, we went over some rules. Remember, if it is top heavy, there is no horizontal asymptote. If it is bottom heavy, the horizontal asymptote is y equals 0. And if the numerator and denominator have the same degree, then you must get the ratio of the leading coefficients. But for that, you can refer to the previous slides. So for number 6, we plot at least one point between and beyond each x-intercept and vertical asymptotes, because we want to know what kind of behavior the graph has. Number 7, you use the information obtained previously to graph the function between and beyond the vertical asymptotes. Here I'm going to go ahead and add another one, and this will be a very good use of your calculator. So you graph your function with the calculator. Of course, if you ever end up taking a class where you're not allowed to use graphic calculators, like it may happen to some of you in the future, then you might want to refer to steps 6 and 7, and so just plot some points and to see what's happening between any vertical asymptotes or horizontal asymptotes. So let's go ahead and we're going to graph the function here. I need to make some room. And the graph that we're going to graph is here. The function that we're going to graph is here. So we're going to follow the steps. Number 1, it says determine whether the graph has symmetry. So for that, we're going to find f of negative x. So if I do that, I need to substitute every x with a negative x. And after doing that, I will end up with negative 2x minus 1 is equal to negative x minus 1. And you can see here that if we compare that function to the original function, they are not equal at all. And we also, so I guess we could say, is this function even? We will say no, because it's not the same as the original function. Now the other question is the function odd? So is the f of negative x the opposite of the original function? The answer is no, because you can see here that 2x is positive here, and here is negative. But 1 is negative, and here it remains negative. So remember when some signs change and others don't, then we cannot say that the function of f of negative x is the same as the opposite. So in this case, the function is not even, it's not odd, so we will say it is neither. And therefore, it has no symmetry. So let's move on to step number 2. And step number 2 is to find the y-intercept by evaluating f of 0. So f of 0 will be 2 times 0 minus 1 over 0 minus 1. 2 times 0 is 0, so we have minus 1. 0 minus 1 is equal to negative 1. And we know that negative divided by a negative is positive, so this will be 1. So what this tells me is that the y-intercept is going to be the point 0, 1. So that is something important to consider. So let's go ahead and plot it. So 0, 1, it goes here. Now let's go ahead and move on to number 3. And so we need to find the x-intercepts, if any. So we're going to take the denominator of that function that happens to be x minus 1. We equal it to 0. And then we solve for x. So x is equal, I'm sorry, not the denominator, but the numerator. So remember, this refers to the numerator. So in this case, the numerator is 2x minus 1. So we take 2x minus 1 equal to 0 and solve for x. So negative 1, move it across, turns into positive 1. The 2 is multiplying to the x, so what we need to do is divide by 2. So x is equal to 1 half. And so that will become our x-intercept, 1 half comma 0. So that point will be somewhere here. Now we move on to step number 4. And so for step number 4, that is where we need to get the denominator. And that one happens to be to find the vertical asymptotes. So we take the denominator that happens to be x minus 1 equal to 0 and then solve for x. So x equals to 1 will be the vertical asymptote. Okay, so we're done with number 4. Let's go ahead and move to number 5. And now to find the horizontal asymptote, we need to consider, is this function top heavy, bottom heavy, or is it of the same degree? And so you can see that the degree of the numerator is equal to 1, and the degree of the denominator is also equal to 1. So because both polynomials have the same degree, we're going to have to get the ratio of the leading coefficients. So the leading coefficient of the numerator is equal to 2, and the leading coefficient of the denominator is equal to 1. Remember, this is what I'm talking about. And so 2 divided by 1 is equal to 2. So that is going to become our horizontal asymptote, 2. So we're done with number 5. Now let's move on to number 6. Number 6 says plot at least one point between and beyond each x-intercept and vertical asymptote. So what we're going to do is use the table that I have here. And so you can see here what's happening on the left side of the vertical asymptote. So when x is equal to negative 2, you get a y value of 5/3. When x is equal to negative 1, you get a y value of 3/2. And so we're going to use that information to finish out plotting our graph. So when x is negative 2, the y value is positive 5/3. And remember, 5/3, that is a little less than 2. When x is negative 1, the y value is 3/2. So that is like 1.5. Now when x is positive 3/4, so now we're moving to the right side of the vertical asymptote. So 3/4, the y value is negative 2. I'm sorry, we're still on the left side of the vertical asymptote. 3/4 is still less than 1. So when the x value is 3/4, the y value is negative 2. Now we're going to see what happens on the right side of the vertical asymptote. Remember, the vertical asymptote is this green line with the equation x equals 1. So when we get to x equals 2, we're looking at the right side of the vertical asymptote. And so when x is 2, the y value is 3. Also, when x is 4, the y value is 7/3. And 7/3, it's a little bit over 2. Now, I want to remind you that we cannot cross those vertical asymptotes, horizontal asymptotes sometimes, but not the vertical ones. And so that is the graph of the function. If you are not sure, you may use your calculator to check your answer. So we're going to go to the next slide and graph the next one. And what I would like to do here, I prefer to get the vertical and the horizontal asymptotes. I think those are very good points of reference. So to obtain the vertical asymptote, we take the denominator, x squared minus 4 equal to 0, and then we solve for x. So what I'm going to do here is factor that difference of squares, so it's x plus 2, x minus 2, and equal to 0. After that, we take each factor equal to 0, and then solve for x. So we have, in this case, we have 2 vertical asymptotes. One is located at x equals 2, and the other one is at x equals negative 2. After that, what I would like to do is find that horizontal asymptote. And so we could see here that the degree of the numerator is a 2, the degree of the denominator is also a 2. So in this case, we have to get the ratio of the leading coefficients. The leading coefficient of the top is a 3. The leading coefficient of the bottom is a 1. So in other words, the horizontal asymptote will be equal to 3. And so that is my horizontal asymptote. Now, let's see if this function is going to be symmetric. And so to find that, we need to find f of negative x. In this case, we'll have 3 times negative x squared over negative x squared minus 4. And we know that whenever we square a negative quantity, that remains positive, because we're multiplying negative x times negative x, so that will be positive x squared. Similarly here, negative x squared will be x squared minus 4. And so what we're seeing is that f of negative x is the exact same thing as f of x. And because of that, we say the function is even, and even functions are symmetric with respect to the y-axis. So that will be useful when we graph our function. Now let's go ahead and find the x and the y-intercepts. So to find the x-intercepts, we let our function equal to 0. Or y equal to 0. But remember, we had a little shortcut for that, and that was to let the numerator equal to 0, and then solve for x. Well, I'm going to do the long version of that. So if I let f of x equal 0, I will have this. And so I'm trying to solve for x, and I know that x squared minus 4 is dividing 3x squared. So if I take this quantity across, I know that instead of dividing, it will be multiplying. And so that will be 0 times x squared minus 4. and that is equal to 3x squared. 0 times x squared minus 4 will be 0. And then we have 0 equals 3x squared. And so that is why the previous slide is mentioning that shortcut that states that all you have to do is equal the numerator to 0. So then let's go ahead and solve for x. So we know that 3 is multiplying x squared. We need to divide. So we will have 0 divided by 3 is equal to x squared. From there, we know that 0 divided by 3 is equal to 0. And here, if we take the square root of x squared, that will take care of the exponent. We get x, and the square root of 0 is just 0. So what happens here is that the x-intercept is actually happening at the origin, and that is a point 0, 0. Now, the good news here will be that the x-intercept is also the y-intercept. But just to make sure, let's see if this is true. So for us to find the y-intercept, what we need to do is let x equal 0, or in other words, you find f of 0. So if we're finding f of 0, we will have 3 times 0 squared divided by 0 squared minus 4. 3 times, 0 squared is just 0. 0 squared again is 0. And so we have here 3 times 0 is equal to 0. And 0 minus 4 is equal to negative 4. And so what do we get when we divide 0 by negative 4? And the answer is 0. So this confirms that the y-intercept is the same as the x-intercept. And that is happening at the origin. Now, what we could do here is get more points. By substituting numbers. So let's try to do 1 and positive 1. So I'm going to erase this to make more room. So if I try to find f of 1, it will be 3 times 1 squared over 1 squared minus 4. 1 squared is equal to 1. One squared is equal to 1, so 1 minus 4. 3 times 1 is 3. 1 minus 4 is negative 3. And so 3 divided by negative 3 is equal to negative 1. So from here we get the point 1 comma negative 1. Now remember how we established that this function was even, and even means that it is symmetric with respect to the y-axis. So this is where symmetry comes in very handy, and that means that if we have the point 1 comma negative 1 here, this point, we will also have the point negative 1 comma 1. And so what we're going to have here is something that will look kind of like a parabola. Now, to know what happens, let's say on the first quadrant and second quadrant, I'm going to choose a random number that is on the right side of the vertical asymptote x equals 2. So that number is going to be, let's use 3. So I'm going to find f of 3, and that would be 3 times 3 squared over 3 squared minus 4. 3 times 3 squared, so we have 3 times 9, and then 9 minus 4. So f of 3 will be 3 times 9 is 27. 9 minus 4 is equal to 5. And so that will be 27 over 5, 27 fifths, and that is a little bit over 5. So when x is equal to 3, the y value is 27 fifths. And that point will be somewhere here. Now, because of symmetry with respect to the y-axis, I know that that point could also be here. Same y value, but with the opposite x value, so -3, 27 fifths. Now, since I don't want to keep plotting points, I'm going to just use the calculator with my previous knowledge to graph the rest of the function. And so it looks like that. Feel free to use your calculator for that. The next function, I'm going to leave, let's see how many more functions we have. Okay, so let's grab that one quickly. Okay, so for this function, to find start with finding the vertical asymptotes. So we take the denominator, x squared plus 1, equal it to 0, and then we try to solve for x. So x squared is equal to -1. And if we want to solve for x, we know we have to take the square root. But however, even though that will cancel the square, we know that for the set of real numbers, this equation has no real solution. So what that means in terms of a vertical asymptote is that we do not have a vertical asymptote. Now let's see if we can find a horizontal asymptote. And we know that the degree of the numerator is 4, the degree of the denominator is 2, so we could say here that the function is top-heavy. And top-heavy functions have no horizontal asymptotes. So far we do not have those. So what I'm going to do is find the x and the y-intercepts. So to find the x-intercept, remember we're going to use the shortcut, so that will be to let the numerator, which is x to the 4th, equals 0. And here, if we take the 4th root of x to the 4th and the 4th root of 0, that will take care of the radical, so we will get x, and the 4th root of 0 is just equal to 0. So, wait a minute, looks like I did something wrong. Okay, so I didn't do anything wrong. What this tells me is that to be the x-intercept, we know by default the y value is 0. And so we solve the equation and x is equal to 0. So when that happens, we know the x-intercept is at the origin, and that is also the y-intercept. Just to confirm, we're going to go ahead and find the y-intercept by finding f of 0. So that will be 0 to the 4th power divided by 0 squared plus 1. And so that will be 0 divided by 1, which is equal to 0. So that is true. The origin happens to be both the x and the y-intercept. Now remember, we do not have any x or y, no vertical or horizontal asymptotes. However, one thing that I'm missing here is to find symmetry. And to find symmetry, we find f of -x, so that will be -x to the 4th power over -x squared plus 1. And so that will be, we have an even power, so -x times -x times -x times -x is positive x to the 4th power. On the bottom, -x squared will be -x times -x, which is positive x squared plus 1. So since we are obtaining the same function as the original function, we could say that the function is even, and therefore it is symmetric with respect to the y-axis. Now keep in mind that we do not have any vertical asymptotes and we do not have any horizontal asymptotes. So if I was to choose any any x values, for example, x is equal to 1, we will find f of 1, and that will be 1 to the 4th power divided by 1 squared plus 1. 1 to the 4th power is 1, 1 squared is 1, so we have 1 plus 1, and so that it will be 2. So the y value corresponding to x equals 1 will be 1/2. Here. The function is symmetric with respect to the y-axis, so we could also have that point there. Now let's choose x equals 2. And so we will find f of 2, and that will be 2 to the 4th power over 2 squared plus 1. 2 to the 4th power is 16, 2 squared is 4, so 4 plus 1 is equal to 5. So that will be 16 over 5, and 16/5 is a little bit over 3. So somewhere there. Remember symmetry. And so just to finish this problem, because I really want to go home, I can tell you that this is going to look similar to a parabola. If you don't believe me, you may use your calculator. Okay, so the last problem, thank God, for you and me, we're just going to discuss briefly slant asymptotes. And remember, we already talked about vertical and horizontal, so a slant asymptote is something that is slanted, like the line that I'm tracing. And so those happen only on top-heavy functions. Remember, top-heavy is when the degree of the numerator is higher than the degree of the denominator. And what we know here is that there's nothing we can cancel here, because here we have a sum of squares, not a difference of squares. But what we could do is divide. And we could either use long division or synthetic division. So in this case, I'm going to choose to use long division. And so if I divide that by x minus 1, remember we divide x squared divided by x, and that is equal to x. Then we multiply. X times x is x squared. X times -1 is negative x. And then what do? We subtract. So this turns into negative, this turns into positive. Combine like terms, those two cancel. 0x plus x is equal to x. We drop the next term, which is a 1, and then we divide again. X divided by x, and that is equal to positive 1. Then we multiply, so 1 times x is equal to x. 1 times -1 is equal to -1. But now we have to subtract, so we change the sign to negative and this one to positive. By doing that, we combine like terms, those two cancel each other, and then if we add 1 plus 1, we get a 2. So in this case, we have a remainder. Now, I'm going to use the same model that I have here. And so to rewrite my rational function, I'm going to use the quotient, which is here, x plus 1, that is this part here, plus the remainder, which is a 2, over the divisor, which is x minus 1. Okay, and what we get here, it looks like a linear function. So that one is going to give me the slant asymptote. And that is the line that you see here. If you check, the y-intercept is a 1, that would be this point here, which actually should be an open point, open circle. And the slope is a 1. So that means that from the y-intercept, I can go 1 up, 1 to the right, 1 up, 1 to the right, 1 up, 1 to the right, or similarly 1 down, 1 to the left, 1 down, 1 to the left. So that is how you get your slant asymptote. So we're going to do one problem, and this is the last problem. So let's solve example 8 now. We have x squared minus 4x minus 5 divided by x minus 3. So let's go ahead and start by finding the horizontal asymptote. We see that the function is top heavy, so there is no horizontal asymptote. Now let's see if we can find the vertical asymptote. So to find that, we take the denominator x minus 3, equal it to 0, and solve for x. So the vertical asymptote would be x equals 3. Now to find the slant asymptote, we have to divide. Now the denominator is equal to x minus 3. So what I could do here is I can use synthetic division. But if I do that, I need to change the number. Instead of a -3, it needs to be a positive 3. Now I'm going to write down my coefficients, so that those will be 1, -4, and -5. So if we drop the first term, that is a 1, then we multiply 3 times 1, that's 3, -4 plus 3 is -1, 3 times -1 is -3, and -5 minus 3 is -8. So -8 becomes the remainder, and we started with a function of second degree, so the 1 is the coefficient of x squared, -4 is the coefficient of x, and 5 is just a constant term. After dividing by x minus 3, we obtain 1x minus 1. So what I can do here is that the function x squared minus 4x minus 5 divided by x minus 3, it is equivalent to the quotient, which comes from here, and that quotient is x minus 1 minus the remainder divided by the divisor, which is x minus 3. This is just a different form of the original function. But what we do here is we get the slant asymptote from here, because that is a linear function with the y-intercept at -1. That would be here. I'm sorry, that should be an open circle. And the slope is equal to 1, so that means we could go 1 up, 1 to the right, 1 up, 1 to the right, 1 up, 1 to the right, 1 up, 1 to the right. And so, to make this shorter, we can trace our slant asymptote that way. And I don't feel like finding any more points, but what I know, okay, let's just find the x-intercepts. And I want to find them because they would be easy to find. So the shortcut for the x-intercepts will be to take the numerator and equal it to 0. So that will be x squared minus 4x minus 5. So we can factor that numerator. That would be x plus minus 5 and 1. Then we take each factor and equal it to 0. So x is equal to -1. And x is equal to 5. And that's what I was saying, that they're kind of easy to find. So -1 and +5. And then the function is going to look like this. And that's it. That is the end of the problem and also the end of the video and the end of section 2.6.